This and this, isn't it?
Yeah, exactly.
Okay, good morning. First of all, I would like to give you thanks for coming to see us in CIRCE. So it's for us an honor to have this event here, the final event here. So thank you to all of you. I'm going to explain more in detail the 50 kilowatt charger that we have designed, manufactured, and commissioning here in CIRCE. This is the general index that I'm going to follow. General characteristics, resonant topology, image shielding, power electronics, and then some results. Okay. We have designed a 50 kilowatt inductive modular charger. I will explain later why this is a modular charger. You can see that it has two coils instead of one coil of 50 kilowatts. It will be much easier to have only one coil, okay? But due to the questions related with the project, we needed to split in two coils. And at the end, from our point of view, it had given us a chance to develop something different with improved characteristics. The charger allows itself to be integrated with other technologies, DC technologies, like storage systems, batteries, or ultracaps, or generators like photovoltaic or wind generators. We have decided to do the charger a modular charger because we need to feed two different vehicles. We have to feed a type of vehicle that needs between 350 to 400 volts. That is typical for particular EVs, vans, and light trucks. In this case, for the Iveco Daily. And also we need, at the beginning of the project, to feed a bus that needed 700 volts. This is a typical voltage for buses, trucks, and other transport necessities. So with this modular system, with these two coils, we can feed at full power both systems. Okay? The idea can be extended in order to have as many coils with the power that we could consider depending on the necessities of each vehicle. And with this type of configuration, we can switch on only the coils that we could need. Okay? For example, if we could have, for example, 4 or 5 coils on primary side, we could switch on only 2 if needed, only 1, or even we could integrate other power secondary systems with less power than the rest, and even with different frequency. So with this, we achieve the interoperability with any type of electrical vehicle. Okay? We also have designed the complete system in a modular way, so we can independentize every part of the charger. We could change, for example, the grid side and put any other, and it will be very easy to substitute. Okay? To change, I will show that this is a field level, but we could use a commercial one or any other because we have defined the complete system in a modular way. The charger has also the Endesa SmartBox system that Lourdes has said before, and communicates with OCPP. Indeed, it's an extended OCPP because it's special for Endesa. It has some more features that the standard has, and connects with the control center that we have also developed. With this, we can send, or we can see the status of the charger. We can see the actual current status of voltage, current, power, active power, reactive power, if it is on, off, whatever. we can see, we can know who is using the charging station. We can even control remotely the charger. We can give the set point for the reactive power from the DCO control center, or we can reduce the active power depending on the necessities of the grid. Even when the charger is not used for charging, it can be useful for the DSO because we can control the reactive power in always, okay? Even when it is not charging. We have also developed the HMI of the charger. The charger process can be started from the vehicle side or from the charger station. So the driver can go out, put the next button, and start the process, stop the process, and see how it's doing. Okay. So we have two coils. I have said it's more difficult for us to have two coils than to have one coil. These are the size of the coils. With the topology that I'm going to explain, we achieve 30% of misalignment in any direction. They were designed for an air gap of 22 centimeters and allow an air gap variation from 18 to 25 centimeters. We could design it for 30 centimeters, but in this project, at the beginning, we decided that the air gap will be 22 centimeters. And the frequency that we are using is 26 kilohertz. Regarding the topology, you may know that there are 4 classical topologies. The main used is the series topology, but we use one of the topologies that we have patented as a result of the PhD thesis of Dr. Juan Luis Villa, that is not here. And we are using the SPS topology. Okay, why? Well, we have analyzed all the topologies. We have, with this thesis, we have a perfect procedure for designing the resonant topology, and we compare all the topologies. And we saw that the SPS or SPP topology that we have patented has a most safer behavior in any condition. This is, with the misalignment, we can see here that the current, the maximum current, is maximum 20% of the nominal current in primary, 20% of nominal voltage, or 10% of nominal current in secondary. If we compare with series topology, if there is a fail on the control, it could reach more than 2.5 times nominal current, primary, or 1.5 in secondary. So it's a question of safety. The same happens with air gap variation. The SPS topology has always the safer way of working, okay? And with the load is the same. So for to work with high power, we think that this is a very important issue. We have comparison. If we have had this topology, we have used series instead of a series parallel series system. We should need more or less 20% more of copper in primary, more or less 40% more of copper on secondary, so more expensive and heavy. But maybe more important than this, the voltage on the capacitors, on the resonant capacitors, could be 50% more higher on primary side, but 75% higher in the secondary side. okay? So this is why we are using this. Of course, when we design the resonance system, we also design the EMI shielding. The ferrites, aluminum, the size, distance, and so on. And the result that we have achieved is that the measured values are below the expected values. So we always accomplish with the standard INRIP 1998 that is more restrictive than the standard of the 2010. This is power electronics that we are using. We use a 3-level inverter in the grid side. Then we have a buck inverter, 2H in that bridge, and the secondary side. We have also developed, designed, and manufactured the secondary side. The secondary side is a simple one. It doesn't need control at all, because the control is done from the primary side. We have included only a security system that is not shown here, that in case of something happens, we can make a short circuit in the secondary and never will happen anything on the battery, because the system is able to work under short circuit conditions. This is the cabinet. Some of you have seen it several times. Here we can see the grid side, the 3-level inverter with a DSP control, the back with the DSP for the back, the high frequency bridge and the DSPs. The grid filter is a very small grid filter due to we are using a 3-level, so we reduce the size and the cost of the primary side, of the grid side. And I will also say that when we have designed this, of course, this is a prototype, but we have always having in mind that it should be industrialized. So we have thinking on the maintenance uses in order to take the electronic cars and put new electronic cars as needed in an easy way. We have think on the duration of the system, and we have think in a lot of questions related with this. You have here the system working. It makes any noise, okay? And regarding the results, not only is a question of noise, as Lourdes has said, we achieve a very good performance on the grid side. We can control because the 3-level inverter is sized for 70 kilowatts. So we could control from 0 to 70 kVs, reactive capacitive kVs. And we have a very good waveform, because the THD is less than 1% in over the range of running, from 0 to 50 kilowatts. Okay? And the filter that we're using is very, very small, so cheaper. Very cheap. This efficiency is what we have measured in the lab, not in the van, because we have not had time to do the measures on the van. We have had the van only for a few times. But we see that the efficiency in the transmission system is very high, and the total efficiency at nominal power is near to 90%. Okay, for one coil. Okay, I would like to finish giving the thanks to the UNPLUGGED consortium, because we have learned a lot. We have enjoyed very much the project. I would like to thank Axel for the coordination of the project, and I would like to thank Endesa, innovation people of Endesa, that have helped a lot and push a lot, mainly Lourdes, all the days. And I would like especially to thanks to the people of the renewable integration area, because they are really very, very good researchers and technicians. Thank you very much.
Thank you, José. Are there any questions?
Choose the coils of the charger, that you can choose the coils of the charger
No. There is a communication process. When the vehicle comes, it has to say us what is the voltage. Knowing the voltage, we know how do we have to control the coils, okay? If the voltage is 700, we have to control the coils in one way. If it's 350, in other way, okay? This is part of the communication protocol.
Is that communication protocol using the ISO?
Yes. It's using the ISO. It has been developed by Continental.
Any other questions? Yes.
How long does it take to make the communication between the vehicle?
Maybe it could be better explained by Continental. This is a prototype. I think that in this moment, it takes more or less 30 seconds, at this moment, but I know that it can be improved. Anyway, the idea is that when the vehicle is arriving, it starts communication process, starts the recognition, the charger and the vehicle are recognized. The charger can be even, it's reserved for the vehicle that is coming. Okay, and when the charger knows that the vehicle is approaching and positioning, and when the vehicle is well positioned, the driver can start the process from the van or and this should take a few seconds, okay? Because it starts at this moment, we need 30 seconds to start, but when it is coming, it's not time.
This 30 seconds consider also something that happens inside the charger and something that happens inside the vehicle. So from the bare communication point of view, we are currently down to a cycle time of 5 milliseconds.
So we are
cyclically exchanging messages, and the cycle time of sending a message from the vehicle to the charger and get the response currently is 5 milliseconds.
This is 30 seconds is to start communication, and 5 milliseconds is what we are using for controlling primary side, because the vehicle say us continuously what is the power or the current that he needs, and we deliver the current that the vehicle wants. Okay, so he says 40 amperes. We send 40 amperes.
Do you think that this could be used for dynamic charging?
Depends on dynamic charging. Depends on dynamic charging. You know, there are two types of systems. It depends on the size of the coil. If you have short coils on ground, long coils on ground are different concepts. It depends if it is a source inverter or voltage inverter. We are working on one of these, and we are not using. Okay, not for real-time control, but yes, for in order to say to the charger, this is the current that I want, and then we try to do this in short time. Mm-hmm.
Yes?
How did you come to this 5 milliseconds of communication? Is it linked to any safety issue? Because it's compared to the control of the inverter, it's quite a long time.
Yeah. This is the shorter time that it could be assured, in this case, by the wireless communication. So we had some discussions about this, and Conti said us that they could assure 5 milliseconds. So we have arranged the control to be controlled with this time, okay, within this time. Yes, I know it's not, but it's enough, and the system is stable and very safety. It's not a big problem.
My personal view is also that making the communication part of a safety loop is somehow not possible in terms of reaction times that you need, especially when talking about 50 kilowatts. So I don't see that you can rely on communication for safety reasons in that kind of system. So it's, let's say, it's somehow coupled, but not directly coupled.
It's power electronics, which includes the safety.
Yeah.
Yeah.
Yeah. The power electronics includes, of course, a safety procedure to avoid any damage or any risk.
26
Yeah.
So watching the waveforms of current and voltage is much faster than communicating any information. So in principle, this is the idea. Yep.
I didn't quite understand that why did you use 2 coils of 25 instead of 1?
Because at the beginning of the project, this is the original reason. At the beginning of the project, we had to to install this in 2 vehicles. One was the Iveco Daily 350 volts, the other was a Volvo bus. If we had designed only one coil of 50 kilowatts for 700 volts, we could be able to give only 25 kilowatts to the Iveco Daily. Okay. Yes, and in this way we can give 50 kilowatts for both vehicles. This is the original reason, and then we see, okay, it's a good idea.
Okay, then. Thank you, Jose.
Thank you very much, Axel.
I think we now switch over to